Yeah. Today we'd like to introduce the last topic of our unit, which is partial fraction decomposition. The goal of today would be to do the following. All right? I have up here a slightly more complicated example than the warm-up. You can imagine if you started, I've written it in a way that I have, and in a minute I'll tell you why I wrote it in the order I did. Okay? But you might be used to doing the following problem. Take the right side of this expression and combine it, right? Add the fractions. And when you do, you can just trust me, you don't have to do the work. You will get the thing on the right side, okay? But the question I have for you today is, could you, if I give you the thing on the left, make the thing on the right? Yeah. Or, let's forget that. You're like, what? No, whoa. Let's go simpler. Could you even do the warm-up today in reverse? Right? If I gave you 5x plus 1 over, I don't remember what it was. Could you undo it? Could you go backwards and find out what two things were added together to get the thing that you have in front of you? Yeah, could you do it?
Does there also be like many solutions to this?
No, is the answer. The reverse process is called partial fraction decomposition, and that's what we're going to look at today. And for now, it's just like a puzzle for us. It's like, can we figure this out? Like where this came from? You'll notice already maybe from the form of what I have written up here, and I will just guarantee you right now that the thing I have written up here is the best we can do. We cannot break what I have up here is a unique solution, and we can't break it up any more than we already have. Okay? There's no way to like break this down a different way or a better way. And you'll notice that like we have in the denominators maybe you could already make some good guesses about. Like those should look familiar. In fact, that might be the first thing you did if you were going backwards on the warm-up. You might be like, well, what do you notice about these denominators as they relate to the one on the right, to the one on the left, excuse me. I mean, this one on the left factors, doesn't it?
Yeah.
As x squared. So, I mean, this connection times x squared plus 1 is not unintentional, right? This is obviously, there's something going on there. The factors, maybe we expect the denominators to be the factors of the denominator that we're looking for. Definitely a strong relationship there. You saw that happen on the warm-up too, didn't you? Okay, the x squared. Notice that like we have an x though, and we have an x squared. And also notice that x squared plus 1 down here, the best, it turns out, I guess, the best we can do up on top is something linear. Notice that like we have a constant here and here, but here we have something linear on top. Okay? So we're just making some observations at this stage. We still have no idea how one would go from left to right on this. It does look suspicious. There are some 3s and 1s and stuff, but I think that's mainly coincidence. Okay. All right, so I'm going to give you, like, I don't normally, I like to maybe give you more of like a discovery feel normally. But I'm just going to tell you right out how to do it. 5 steps. 5 easy steps, or maybe they're painful steps. And then we'll discover what those mean in a minute here, okay? Because some of these are a little hard to understand. If the degree is, if you have a fraction you're looking at and the degree on top is higher, or actually, I'm going to add this, sorry, or equal, then do long division, okay? And there is, I think, 1 or 2 on the homework that will be like that tonight. But I'm not going to give you an example of that in class today. So start by doing long division and rewrite the thing in fraction form. And then proceed to do partial fraction decomposition on the remainder over the divisor, that piece. Okay. So number 1 is actually not going to come up in our lesson today, in the things I talk about at least. It's pretty clear, if I hadn't told you that you might want to factor the denominator, just because of the observations we've already made. So do that. And by over the reals, I mean, do you remember this theorem from earlier? That we can take any polynomial that might be in the denominator and factor it all the way down to linear factors and irreducible quadratic factors, right? Sometimes we'll have a quadratic that we can't go further and break that up, right? And remember, we called that an irreducible quadratic. So sometimes we'll have to stop at a quadratic. But you never have to stop at a cubic, right? Because a cubic always has at least one more real root to be factored. Fourth powers could always be factored into two quadratics. Yeah. Okay, so this is the part where it gets a little messy. And it's actually not a terrible idea, just hang with me, but the notation is terrible. I'm borrowing the books. I don't really have a better way to write this, so I'm just going to borrow the book's notation. For each time a linear factor appears in the factorization, you need to have a copy of that linear factor with, on top of it, some constant. Now we're subscripting these, but any capital letter here is some constant, unknown, that will eventually be solved for. So in the example I was just showing you, I think we had like, there was a factor of x squared and the denominator wasn't there. That counts as like a linear factor. That's like, you could say it's 1x plus 0 squared, right? It's this form. So that means we need to have a over x, or a0 over x, and a1 over x squared. We need to have every copy of that linear factor all the way up to its multiplicity in the factorization. So if this is to the third power, that's gonna contribute 3 terms to our breakdown. And this is the part that gets really terrible looking. We need to do the same thing with copies that appear in our factorization of the irreducible quadratics we might have as well. So assume for a second that we have some quadratic that can't be broken down. That's what I'm trying to say here. Yeah, maybe we should have done 1 through, yeah, that's weird. Yeah, you're right. Actually, that should be, yeah, it should be 1 or m. It doesn't actually matter. In a minute when we go to do it, we're just going to name them whatever we like. We're going to call them like A, B, C, D, E, F, G or something like that. Okay, and then the big task, of course, is number 5, and that's actually solving for the unknown constants, and that's all those capital letters that we've just written. 1 through 4, though, outlines how we might just come up with the form of the partial fraction decomposition. That is, can we come up with like the denominators, basically. Now notice that for an irreducible quadratic factor, we already made this maybe an observation on the previous slide, that the best we can do for an when we have an irreducible quadratic in the denominator is something linear in the numerator. Okay. Notice that if you thought that we might get something linear up here in number 3, then you'd have something linear divided by something else linear. But of course, if that were true, then you could have broken it down more by using division, right? So you'll always be able to do this well. You'll always be able to get a constant over a linear factor. But if it's quadratic, the best we can do is a linear on top of that. It kind of goes a little bit back to some of our discussions from earlier. When we're dividing, you always expect the remainder to be of a degree lower than the divisor itself. Otherwise, you didn't do enough division. That's kind of maybe the reasoning why that's happening. A lot of this still maybe feels like a little bit of a black box. Like I said, just hang in there. Let's hold off on any question you might have yet until we've done an example or two, and then you're allowed to ask a question, because this is a little weird right now. Always come back to it if you need to, or whatever you need to say. Okay, on these first two, on these first two, I just want you to write the form of the partial fraction decomposition, which means we'll be considering steps 1 through 4 from the previous slide. But we're going to omit number 5, which is actually solving for the constants. And I think in a minute you'll appreciate that because there are a lot of constants in these. So let me handhold on the first one here. Okay. Really, right now, we're going to just kind of disregard the form of the numerator. Really, we're looking at the denominator as our guide. So remember, like I said, x cubed, that's a linear factor cubed, right? That's, if you want to even think about it as 1x plus 0 cubed, you could. I just want to emphasize that this really is still of that form ax plus b to some power. That means we need a copy of x in a denominator, put a letter on top. We need a copy of x squared and all the way up to whatever m is, or whatever the multiplicity of that factor is. So that's all just because of x cubed. The x plus 3, that's another linear factor. We can do with just one constant in the numerator over an x plus 3, and we're done taking care of that one. We still need something to deal with the x squared plus 1. And if you're looking carefully on the last slide, what do we need to write upstairs? This is, by the way, sorry, we should have stopped and said it. X squared plus 1 is an irreducible quadratic, isn't it? That is to say, if you were to keep factoring it, you'd have to use non-real numbers to do it, right? If you factored it, it would be x minus and x plus I, right? Is how you'd have to factor that. So we're not going to go there. We want to stop with anything that might be irreducible. So what goes in the numerator on the last one? Go back to my guide. What did I say? For each irreducible quadratic factor, I need to have. So I'm just making up these letters. Yeah, how about EX plus F?
How do we use E?
Feel free to use whatever letters you like, right? You can use, like if your name is Judah, you can use like J0, J1, J2. They can all be J's if you like. Anything you like. In fact, depending on how you wrote this, maybe, you wrote A over X plus 3. Your A is different than my A, maybe even, right? You started with that one, which is all fine, okay? We'll all come out in the wash in the end. So step number 5. Step number 5, we're skipping right now, but the goal would be, of course, to figure out. You might be like, why would we even do this? So far, we're not done. Obviously, we want to figure in the end out what A, B, C, D, E, and F are, right? So let's do this one now. Yeah. No, we're not actually going to do these two. And the reason is because these have like 6 constants, and that's a little more than I might expect normally. This is just mainly to prove a point about the form, to practice the form. The first couple examples I'll give you have like 2 unknown constants. 3 to solve the worst. Yeah.
So, will we have homework problems similar to this?
Homework problems similar to this? Yeah, there are some I think in the book that do ask you the same kind of thing. Find the form of the partial fraction decomposition, but do not solve for the coefficients, for the actual constants. All right, so we're coming up with this factorization, the denominators we need and all that down here. I mean, I did most of the work for you, right? There's still a little bit of factorization for you to do. Remember, the numerator doesn't really matter to us right now. So let's see here. So what do we have?
So x minus 2 and plus 2.
Yeah, we need an x minus 2 and an x minus and an x plus 2 as our denominators.
Oh, so that's how you do it.
Right? If you factor that.
That's just guessing.
So that's linear, right? You got A and a B, how about? And maybe you put them in a different order. I think in last class I had these out in a different order, so it might be different for you.
And how do you do the next one?
All right, so what about x squared plus 3? X squared plus 3, I'm trying to make it at least at this stage it's obvious that x squared plus 3 is an irreducible quadratic. Is that obvious to you?
Yeah, but x
Okay.
X squared plus D over X squared.
So we have cx plus d over x squared plus 3. And then this is if you understand what I'm about to write next, it means you understood bullet point 4 on the previous slide. Right? It said not just for linear factors do we need to do this repeated stuff.
Oh, and then you write the x squared plus 3 squared.
We also have to have x squared plus 3 squared. And if it was to the third, we'd have to do it again, right? And on top, we need ex plus f. And again, in this particular example, we actually still have, we have 6 constants again to solve for.
I disagree. I got JX.
All right. Whatever you like. Okay, so again, it's still a little bit opaque, maybe. You're just trusting us that this is going to work for us.
I know.
Let's actually do one all the way through, including step 5 now. And on this one, I think the actual form of the partial fraction decomposition comes pretty easily, right? That's not the hard part of this one.
Now we're actually finding.
Now we're actually going to do it.
Oh, that just means we put it on top.
So
I got it.
we need to start by doing, now step 1 we don't have to think about, right? We don't have any division that could be done here. Step 2 is to
You put 5x plus.
factor the bottom, and that factors as something x minus 5 and x plus 3, okay? And then, like I said, this is not the difficult part, hopefully, on this one. The form of the partial fraction decomposition is nice. This should actually kind of remind you of the warm-up a little bit. It isn't the warm-up problem.
Wait, but don't you fill in the in?
But you might have even started with this assumption if you were trying to work backwards on the warm-up, right? You might have been like, well, I think just from my prior experience that it's probably adding these two things together, right? Something of this form plus something of this form, right? You're trying to work backwards on the warm-up. This is not the warm-up problem. It's similar. All right, but now our goal is we're not done yet, right? That's good. We're in a good way. We have it very clear in our minds. We have it very clear in our minds what our goal is now. Our goal is to figure out what A and B are, right? And once we've done that, we'll be good. We'll have done it. So let's do some work here. Let's just play around. I'm going to multiply this whole thing by x minus 5 and x plus 3. Top and bottom, both sides. Oh, excuse me. The whole equation by that. Just to clear out the denominators, I'd rather not deal with fractions.
Oh, okay.
Okay. So the whole thing. Over here, that kills the denominator on the left, and that kills these denominators too. We get a times x plus 3 left over, plus b times an x minus 5 hanging on. So far, so good. And let me just step back a moment and look up at the thing in the parentheses that we first wrote down. Remember that this is supposed to be an equality, always, for all x. Like if you plug in x equals 10, you get some true statement, don't you? Should be true for all values of x. So if you plug in x equals 10, it should be a true statement. You could also plug in negative 17, get another true statement. Okay? Let's keep that in mind down here too. I'd like to plug in an x value right now, just for fun mainly. Okay, you ready?
2.
0.
Anything you like. Yeah, 0, 2.
0.
How about 5? Yeah, I like that.
Why would we plug in such?
Because it's a 0.
All right, if we plug in x equals 5, then over here we get 5 times 5 minus 1. And over here we get a times 5 plus 3 plus b times 5 minus 5. I like that. And so, reducing this equation to what it really says here, what do we have? 24 equals
A to the
8a.
8th. No, 8A.
Therefore, a is 3. Anyone else want to make a slick choice
-3.
of x? How about maybe -3?
So I was voting for first.
You were voting for that one? All right, so let's just do this a little more quickly. If we plug in -3, we get negative 16 on the left, and on the right we get negative 8b. Yes?
So net 2.
If you plug x equals -3 in. So therefore b is 2. All right, so this is cool. I think we did it. We got 3 over x minus 5 plus 2 over x plus 3. And furthermore, so there's the partial fraction decomposition. And furthermore, you can check your answers, couldn't you, by adding them back together in the same way you did in the warm-up today. And check.
Did you guess and check at the beginning? Did you see 5x minus 1?
I don't know that guess and check would be a really fruitful strategy.
Worked for me so far.
All right. especially as we get more complicated. If you want a name for this method, it's called one nice name for this method is called the Annihilator Method. You like that? Bam, kill the 3. Bam, kill the 5. All right. It's called the Annihilator Method. Yeah, it's the name that a lot of people give it. It's also called the Heaviside Method, named for the mathematician.
I thought you were going to say it's the chase method.
No. Peter?
So what do we use this?
Mainly right now, like I said, it's a puzzle, right? Isn't it a fun puzzle? Yeah. I'll tell you, no. Peter asked a good question you might be having too, because especially in the next example as these get messier, you might be like, please, why are we doing this? So the answer is right now it's just a good puzzle, and I hope you appreciate that. Like, that's a good question to ask. Like, isn't that a fun question? Where did this come from? That's like a good question in its own right. Just for fun, right? It's like, go, figure it out, right? Maybe that's good enough. But the other answer is one that you're not going to like as much, and that's that you need this for calculus. Right? It turns out that this first expression is very difficult to deal with in a certain context in calculus, and this expression is quite easy to deal with. All right? We'll just go with that. But right now, it's rational. We're talking about rational functions. We might as well have some fun and ask the question now. All right, let's do another one. It's getting a little nasty here. All right, so hopefully, again, the actual form of the partial fraction decomposition is not like the challenging part necessarily of this. So we have a over x plus, anybody?
X squared over,
Yeah.
no, yeah.
Yeah, we need a bx plus c because x squared plus 4 is an irreducible quadratic.
What? That was correct, though.
Okay, and then, by the way, is there a way to know whether I've been giving you these really nice ones, x squared plus 4. It's really clear that that's irreducible. Is it obvious when it's something that's like of the form ax squared plus bx, where b is not 0, plus c is an irreducible quadratic? How do you figure that out? Yeah, you have to check the discriminant, right, to see whether it has non-real roots, maybe. Okay. Just saying. All right. I'm going to clear the denominators again. That's what I'm going to do.
So you're going to multiply by x.
Okay, are we there so far? So good? But already, I think, stare at this and realize that maybe our previous method is not quite as slick on this one. Maybe we could make some good choices of x, and actually maybe that would still work, and that's okay if you want to knock this out a little bit. But I want to show you another method. I want to show you a second method that you might like as well, okay? For solving for the constants. We're going to give you two methods today. The Annihilator Method and the method which is yet to be named, okay?
Can we name it?
No, we'll name it for you, but only after we do it, okay? I want you to multiply this out here. So far, so good. All right, and then I'm going to do something a little bit interesting on the right side. I'm going to collect like terms. Are you ready? So we have the x squared has a coefficient of a plus b. Cx, that's our coefficient on the linear term, and then our constant is 4a. And then I just want you to stare at this for a second, the thing in front of us, and like have an epiphany. Keep in mind, remember, this is an equation. This is true for all x. More important, the polynomial that sits on the left side is the same polynomial that sits on the right side. With that in mind, what must be true about a plus b? What's a plus b?
A plus b equals 5.
C is,
A is negative 1. A is negative 1.
all right? This is, now I'll give you the name for this method. It's called the method of corresponding coefficients. Is that a good name for this?
Yes.
This is the same as this because they both are the corresponding coefficient on x squared. All right, now at this stage we have a system of equations in 3 variables, okay? But it's not a huge chore for us because we have C, we have A, and B is, what's B? What's B then? 6. All right. So what do we have? Negative 1 over x. All right, I know it's exciting. I know.
Are you still trying to catch up on the work? And then I'm like,
All right, so once again, we claim that we're right. If all the algebra went well, then we are right. If all the algebra went well, then we are right. But if you need some confidence, feel free to add these back together on the right side and see that in fact you do get the thing on the left. Okay? So let me just give you a word about the 2 methods that we just talked about. We're going to do one more problem to close up the period in a second, okay? But let me give you a word about the 2 methods. We learned the Annihilator Method, and then now we've just talked about the method of corresponding coefficients. And the method of corresponding coefficients, the one we've just been doing here, works for everything. So let me just say that. Okay? We really like the method of corresponding coefficients, but the Annihilator Method for cute little ones that have like 2 constants is pretty cool. And it is kind of fun, and it is called the Annihilator Method. So you may still want to do whatever you like to get the job done. So the point is, the Annihilator Method is not real great here, but the method of corresponding coefficients would work on the previous one, right? You could go back and do it. You could have gotten, yeah. You could have gotten some work from the Annihilator Method. All right. Shh, last one, promise. Stay with me. Here we go. All right, now there's not too much in the way of factoring to think about here. That's another nice, fairly obvious irreducible quadratic again. So we want to break that down in the way that we've been kind of promising that it would be broken down, and that's how. How's this roll? How's this go? Keeping in mind what we did earlier. You want that, Peter?
Ax plus b over x squared plus 1, and then cx plus b over x squared plus 1 squared.
Good, yeah. So is everyone else with him? Yeah, so okay, we're stepping it up here. We got 2 constants that were unknown, and now in our next example we had 3, and now we have 4 unknown constants to solve for. This is going to be fun. But actually, I promise this one's going to work out kind of nicely. You're going to like this. Okay. I'm going to do the same thing as always. In fact, the method, you could probably just run with this. I mean, you guys just did the previous one. I'm just going to do the same thing again. X plus 1 squared. Okay, multiply through by that. Notice here that we still retain 1 copy of x squared plus 1. Then when we multiply, and over here both cancel out.
Yeah.
Okay, good. Keep going. Multiply the right side out. We're going to correspond coefficients again. Ax cubed plus bx squared plus a plus b plus c. All right. Are you with me? I'm going quick here. Let me make sure everyone's. Let me pause for a second. I'm going to collect like terms on the right side again. A plus c is an interesting coefficient, and b plus d together is the constant term.
Wait, what?
Yes? Yes. Everyone. So, therefore, if again, these really are the same polynomial, then what's a? 0. Yeah.
So
Yeah, we
A
might
plus
have
0,
to
you can
might have to make that conclusion. Let's see here. B equals
B equals 3.
3. A plus C is equal to 0.
So C
And
equals 0.
and B plus D is equal to 4. Okay, so like I said, theoretically at the end of a problem like this, you could actually have 4 equations that were like hard to solve. Right? But maybe not. A is 0, B is 3, C must also be 0, and D, we don't know yet, is must be 1. Okay? So I know I promised that we need to have these A and C constants in here, but in this particular example they both zero out, alright? And that's gonna maybe happen. You can't guarantee that will happen, but it just did. So we have this as our fraction decomposition. 1 over x squared squared. Alright. Alright. How do you like that? Is that good? Are we having fun yet?